Now, I've told you enough that if you had come in here not knowing anything about SPH, you would now be able to go home and write programs which would enable you to study the dynamics of binary systems or something else. You could do this. I haven't told you how to calculate the gravitational field, but you could try something crude, but you could do it all. Now I want to talk about something different. I want to talk about heat transport. And the reason why I decided to do this is because heat transport involves a second order differential equation, and there are some points about it which I think are interesting, some computational and some concerned with how you set up the equations. And the exciting thing is I've now got some better pens. Here is, I'll use red because it's heat. du dt, this is thermal energy per unit mass, is equal to minus, I'll get the notation right here, 1 on rho div, that's should be a kappa, grad T. Now this is a heat conduction term. This guy here is thermal conductivity, which I'm treating as a scalar. It's more difficult if it's a tensor, and it may be dependent upon the temperature. And if it's radiative transfer, you would have a similar sort of equation, but this term would be complicated. So I'll just write it down. Thermal conductivity. Now, this is the, I'll just write that down too, thermal energy. In the equations of fluid dynamics, it's possible to, the thermal energy will change because of viscous terms, and it will change because of the pressure can squeeze things up and make it hotter. And there may be sources of energy, radiation coming in, loss of energy, radiation going out. But this is a simple kind of equation which has some certain features which I quite like. For example, one of the things I liked doing with this was studying freezing. You have water there, it gets cold, ice forms at the top, there's an interface, and people worry about how to get the conditions across the interface. And it turns out that with SPH it's all very simple. You just have to do a few simple things. And so it was really nice trying to study this. Then a friend of mine who works in Sicily used the same technique for lava flows, because lava is hot and molten, but near the top surface it forms a crust, and you have to take into account the thermodynamics of the crust forming. So there are many interesting problems, I think, and this we can write as CP, it's a specific heat at constant pressure, rate of change of temperature, following the motion actually, is equal to 1 on rho div of kappa grad T. Now we have to think how we're going to calculate this. There are second derivatives in here, and the first thing you might think of is that you'll write this as grad kappa, so we'll take the gradient of this, dot grad T, plus kappa del squared T. And then you can ask yourself, can I write this in SPH form? Incidentally, this is derivative following the motion, so it includes advection. So the heat is transported not only by some conduction, but also by transport. And that's buried in here because that's partial derivative with respect to time plus a v dot grad term. So the advection comes into that. But I'm not going to think about that at the moment. I'm going to think about just conduction in some static material for the moment. The SPH form most obvious is that Cp dt A dt is equal to, now there are various terms, I'll just do one of them, one on rho, and I'll work out a gradient using some SPH summation. I won't go into that. I want to look at the second derivative term up here. So the question is, that I want to raise with you is how do we find, what's a good way to find the second derivative? Now there's simple ways of finding a second derivative. I sometimes tell you things that are no good, but there are reasons for this. Consider del squared t. This is the second derivative of an interpolated form of t. So I write that sum over the other particles, mass of the particle I'm considering, density t. This should be b, tb, w, Ra minus Rb. Often in this I'll take derivatives with respect to r because I'll leave an r in there, but in the end I will often have an Ra. So I want a second derivative of this. Now where is the coordinates of particle A? They live in here. So I can actually just put this through Tb isn't involved with this derivative and have del squared of the kernel. Well, that's simple. I'll do it with respect to the coordinates of particle A. That's a simple thing. And then I could find the gradient of this in SPH form. I won't write that down. I could find, you only need to write a certain amount of this down because I'm going to say in a minute, don't do it. Grad T, you can write that down as well. And that looks okay. Maybe it's accurate to order h squared if you're using the kernel, like delta x squared. But the trouble about it is that you want it to be such that the interaction between any two particles is such that the heat goes from the hot body to the cold body. So you should be able to look at an interaction term. Here I've got A. I look into this with all this stuff and I say, what is the contribution of particle B to this? Well, this particular term, apart from the kappa, involves this del squared. Does that have the property that if temperature at A is greater than temperature of B, heat will flow from one to the other? Depends on the sign. That's one thing. And the other thing is, does it guarantee that the entropy is going to increase because of this conduction process? Now usually students have done some thermodynamics, but they're a bit frightened of entropy, a kind of mysterious thing, and they probably think who cares anyhow, but it does lead to changes in stability, and it won't work for this. You will find the entropy won't increase. So the most obvious thing is in fact no good. Doesn't guarantee heat. Oh, wait a minute. Heat goes from hot to colder. So I'm telling you these things because I don't need to give all the details. I just need to give you hints about what you should think about. So you have to think about what to do. Well, I played around with this, and the way I get it was to use an integral form. Integral form. That's RAL. And this is an odd thing to do. I want to get a del squared, but instead I look at an integral and figure out that if you look at the structure of the integral, it will do good things for you. So instead of having that, I look at this integral over the space. Now let's see what I've got in here. I have a kappa at r plus a kappa at r dash. So there's a sum of those two. You only get this by playing around. Sort of in the morning you get out some sheets of paper and you try this expanding things and working at it. Now over here I have a TR minus a TR dash. So I need temperature differences. And I have R minus R dash dot the gradient of the kernel, which has got an argument of R minus R dash. Then when I'm playing around, I discover I need a normalizing factor squared. And I think that's all I need in here at the moment. Yeah, that's very beautiful. And let me see if I have got this down right. Da, 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 da. Yeah. Now this, if you expand it in the Taylor series, so you expand this in the Taylor series and you get terms that involve x minus x dash, y minus y dash, z minus z dash, and expand it all out, you find that you get minus the divergence of kappa grad t. Plus errors of order h squared, actually. Isn't that nice? So you get the divergence of the kappa and the other term by doing this. I'm not going to work it out for you, but if you want to work it out, do it in one dimension first of all. Then do it in 2 dimensions just to confirm that everything is all right. So instead of having this stuff like this on the right-hand side, I'll now have this, but I'll write it in SPH form. Da 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 dr dash. Can everybody see that? Yes, possibly. That's the volume element. So in the usual way, I'm going to divide that by rho and multiply by rho, and that's going to be a mass. So this is equal to 1 on rho A times the sum over B, mb over rho B, kappa A plus kappa B. So I'm doing this not for R, but for particle A. Then I'll have a TA minus TB. Now I have this stuff, but I'm going to write Q dot grad W is equal to, oh, well done. Q dot grad W is equal to some F, yeah, that'll do, some F term. I think I'll use that notation. Let me just see if I use this notation. Yes. But well, if I do it right, it should just come out to be FAB, I think, here. Q dot grad W should be FAB. No, sorry about this. I think I want to write grad W is equal to QF. So Q dot grad W is equal to Q squared F. That's right. And Q is R minus R dash. So when I have this in here and I write grad W as some vector QF, actually it's in the direction A to B or B to A, this will be Q dot grad W is give me a Q squared, and that for this is a Q, so that's a Q squared, and that all cancels, so it's got FAB. Now, FAB is related to the gradient of a kernel like this, and you can easily show that this is less than or equal to naught. Take a Gaussian and differentiate it, and for example, x times d dx, I've got to take a kernel which is a Gaussian, and I'll find its gradient. That's equal to minus 2x squared e to the minus x squared. You guys can't see that, but trust me. And that's negative. So that actually is the reason for the sign here being less than or equal to naught. So this expression is the right-hand side of this. So the trick is to have looked for some integral from which I can recover this. And the good thing about doing this is that this involves second derivatives. And they're buried in this, but they're easier to work with. So when you go home tonight, if you haven't already done this, you can just check out. You can go from here down to here. So now I'll write down the whole heat equation, which I'll now do in red. And for particle A, it'll be Cpa dTA dt, derivative following the motion, is equal to the sum over B, mb, rho A, rho B, kappa A plus kappa B, TA minus TB, I like that because it's simple. In SPH, everything that's simple is right and everything that's complicated is wrong. That, incidentally, that's a Russian proverb, I understand. All right, it's simple, but is it good for anything? First of all, this is negative. Everything else in here is positive. If A is greater than B, with this negative quantity here, if A is greater than B, this will be negative. So the contribution to A will be negative. That is, heat will flow from A to B. And so that guarantees this very simple rule: heat goes from hot to cold. Secondly, you will notice that if we sum this, this is per unit mass, so we have to write per unit mass, Cpa dTA dt is equal to, now I'll have MA, and there'll be an MB here. I'll have a rho A, rho B, kappa A, kappa B, and FAB is symmetric. You'll just have to trust me for that. But this is anti-symmetric. So the double summation is 0. It's because of this. When it's anti-symmetric, the double sum is 0. When it's symmetric, the double sum is not 0, which is equal to d dt MACPA TA. And that's equal to naught. So it means that this quantity is constant. It means the thermal energy is conserved. I've worked this out for a case where the heat is only exchanged between the particles. If you have a boundary, then the heat can be transferred to boundary. And there are various ways of dealing with that. But of course, if you have a boundary, the amount of heat inside a container may go down and go up depending upon the boundary temperature. But if you have an astrophysical problem, forget radiation for the moment, or an isolated fluid, then this quantity should be constant. So this expression gives us that, which I think is quite good. So the properties. One, heat goes from hot to cold. 2. I'm now going to have a look. Oh, heat is conserved. So I'm just going to put in here isolated fluid. Isolated fluid. And the other thing is, I'm going to calculate the entropy. So I'll actually write this down on this list. So the total entropy is greater than or equal to naught. This is another one of these rules I mentioned that you really want to have these correct. In a shock you have to have this as well, entropy going up. Well, we'll have a look at what the entropy is. Now, let's give ourselves a heading. Entropy. Fluid dynamics tells you that TdS is equal to du minus p on rho squared d rho. Now we're just actually going to concentrate on these guys. So TdS is du, so this is really T ds dt. And this is really T ds dt. So therefore, Ta dsa dt is equal to all this stuff over here. All this. I guess I'll put it in. Why not? I've got rho A, rho MB, rho A, rho B, TA minus TB, and then this quantity FAB, which is negative and is associated with the gradient of the kernel in this way. All right. Now I want to get this guy, so I have to divide by TA. Here we go. Naturally, I'm not going to put this down again. Naturally, I'll put all these down. And then I have TA minus TB over TA. Yeah, FAB. Now that's all allowed. Now, I'm going to multiply it by MA, because that's actually entropy per unit mass, not per unit volume. Then I'm going to sum over all these guys. And the sum of MA times SA is the actual total entropy, because this is the entropy per unit mass of particle A, this is the mass of particle A, and this is the sum over all those particles. So it becomes, this is supposed to be the total entropy, which is sum. So the total entropy is the sum of the entropy per unit mass of each particle times its mass. So this becomes the rate of change of this, and our aim is to prove it's positive. Now I've done a sum there. That was a sum over B, so this is sum over A, sum over B. And I put an extra MA in there, so now we have a MA, MB over rho A, rho B. And we have this guy. And then we have this stuff. We won't put it, we'll just put all this down here. So we want to show that that's greater than naught. That's what we'd like to do. Well, whenever you get these double sums in SPH, you should think about things like interchanging the labels and getting an expression which is identical, but maybe some of the things have been changed. So that's what I'm going to do. I'll go all the way over here. So I'm interchanging labels, then I'll which shouldn't change anything. Then I'm going to add it to this, which should be the same thing. That is, interchange the labels here. I get a new expression. These don't change, these don't change, these don't change. These two change. A becomes B, and FAB actually is symmetric. So, I get half sum over A, sum over B. I'll write all these terms in, because if I write them in, you've got time to think about things. That's why it's better if you write on boards, because people have got time to think while you're writing it down. That's my theory anyhow. So I interchange these, so this will be, what will happen is, I keep saying this, yeah, that's all right, and I've divided by TA, so there's a TA down here. So when I change A and B, the term that was 1 on TA remains the same, but these will be interchanged, so I'll get minus 1 on TB. And I'll have FAB. These are all positive. What's this term here? TA minus TB. This is the thing you give students in first year, of course. TB minus TA over TA TB. Now that's minus TA minus TB all squared. So it's a negative quantity. So this is less than naught. And this guy here is less than or equal to naught. So the product of those is positive. These guys are positive. This is greater than or equal to naught. Everything's positive. And I've only done this because it actually ensures that the equations have got some important property of heat conduction. But I've done it because I wanted to show you that if you take an integral, sometimes if you can see the structure, it will reproduce something which is a derivative. And that may be good, or it may not be good. In this case, it's very good. We use this first of all for a number of problems, but in particular, we were also interested in what happens if this is very large. So you have very large heat conductivity, and you know the time step, I'll now just go off on a tangent, delta T is approximately delta x squared. This is kind of, if it's a grid, it's the spacing of the grid. If it's SPH, it's the particle separation, more or less, over some kappa. So as you make either delta x much smaller or kappa large, this becomes a very small time step. It may control the time step of your entire calculation. And you have to also find some way of getting around that. But there's another thing which you have to think about too. What if you have a K very large, K, oh here K small. So K is discontinuous. What are you going to do now? You've got these derivatives in here, really, buried in there. So you have to think of some way of handling that. What I did was to actually use finite differences first of all to see what happens at the interface if you have a very simple rule for the gradients. Because what you should have is that this quantity, which is the flux of heat, should be continuous across the interface. So if K is big on one side, the gradient has to be small. And that's because you can't have heat sort of piling up at that central position. So we need to know what happens. So when K is discontinuous, replace Ka plus Kb by 2 Ka Kb. Actually, not 2, 4. So if K is a constant, it's in there. If K was a constant, this would be 2 times the constant. This is also 2 times it. This is, apart from factor half, is the arithmetic mean. This, apart from factor of 2, is the geometric mean. Harmonic mean, I should say. So that's the harmonic mean, and that guarantees continuity. So you can try this out. Heat conduction with the two materials, or the two fluids, one has a thermal conductivity of 10 to the 6, the other has a thermal conductivity of 1. And for some of these problems you can solve them exactly, and everything fits very nicely. Just a simple little change is enough to make it work well. Yep, we've proved the entropy is constant, we've proved that it converges, and we've learnt all this because we kept in mind what we need to conserve, and we've decided to try have an integral instead of just writing down expressions for the second derivatives, as you would do with some of this. Now, there's another kind of equation. I'll just mention one other thing. You can have sources and sinks of heat. Maybe your radioactive materials, maybe you just put something else in. And then Cp dt is equal to divergence of kappa grad T plus sinks, sources. And they may be point sources. I think actually over here I use point sources. Yep. So they have a certain magnitude. There's the rate of change of heat, and we have a delta function in here. So you have a region, and here's Q1, little source, here's Q2, and so on. Or it may be distributed, but anyhow, for this particular case, I'm going to assume that you've got these point sources. And what we will do is replace delta by a kernel, and then we will have our expression here will include, I can just put it straight across. Now I don't have to use the same kernels as before, and I can give them a different length scale, but anyhow, is RK. I'll put H in here for whatever is the length scale. So we need to be able to integrate it with that, and that won't work properly. So I have to put a scaling constant in, or a normalizing constant. And the reason I have to do that is I want the rate of change of heat to be correct. So if I want it to be correct, what I must do is ensure that the rate of change of heat is equal to the rate at which it's coming in. Actually, I've added it to this. I forget which. I'm running out of board space. Look, sorry about that. Let's have a, I'm really down here, aren't I? Oh, how embarrassing. Never mind. I'll just go down to this and put C to K is my normalizing function and a W, R minus R, K, and some scale, length scale. Now, so I shouldn't have had that there. No, I think I'll clean off this. Okay, I'll go down to this, but now I'll have to add this in. So now, the MA, sum over A of MA CP of particle A dTA dt, which that can be written as the rate of change of thermal energy. So I'm doing this. I have those terms, which when I sum over M will vanish, because all that's the internal exchange of energy. And I've got this guy over here. Let me say that again. This is naught because this term, when I sum it over A and multiply by MA, will vanish. But now I have this extra source term. And that will give me, when I sum, and a sum over K, QK, is going to be RA minus RK. And I won't put in the H this time. Now I want this to behave correctly. And so what I want is really the following. A, where is A? A is here, C to K. Let me just see if I've got any other terms. MA, no, this will do. So this guy here, I sum over all the A's, is just something that depends upon the coordinate of particle K. So I choose this, so this goes to 1. So Z to K is equal to 1 over the sum of MAW AK. And then that is equal to the rate of change of thermal energy of the systems, of particles, is the sum over K, QK. And I'll just check that I've got all my lovely terms in here. Yep. So the rate of change of the thermal energy just depends upon the sum of the rate of changes from these sources. And Z to K is given by that as just a normalizing factor, which should be close to 1. And the reason that we've done this is just another thing to notice. We wouldn't get conservation if we left that out. So we put it in, and it's nearly 1, to give it a conservation of energy, because that's more important than having a small error because of having this Z to K in there. And this term should be close to 1. I think I've got a density floating around the place somewhere here, and I'll check that in a minute. I feel I should have a density in here. In row A here, MA, TA. What else did I have? Not a row A there. I think it's all right, actually. One on row A, row B. Yeah. Well, I'll stop with that. I'll check this a little bit later because there are some other things I need to do. And the reason I'm slightly worried is that this quantity is not 1. It would do if it had close to 1. It should have a row A in it. And I don't know where I've lost my row A, so I'm going to leave that as it is and go on to something else. So if you can bear with me while we'll do that. I thought it would be kind of useful to mention something about Lagrangians. In theoretical physics, Lagrangians are used a lot. And sometimes a question of taste, but actually the advantage of using a Lagrangian is that it's a scalar quantity from which you can get vector equations. And it's easier to get the equations from a scalar quantity than it is from just trying to write down the vector equations. Daniel Price and myself wrote a paper in which we discussed the smoothing of the gravitational field. So if you've got you're calculating gravity from the particles, each of which has a mass, but you don't want to have a 1 on r squared kind of force when you get close to them. So you smooth it out. And the question is, how can you smooth it out so that you conserve energy for the entire system? And the easiest way to do this is to go back to the original equations and write down a Lagrangian for them and include a term in the gravity which has the smoothing built in. So then when you calculate Lagrange's equations from your Lagrangian, you will find you conserve energy, and then you get an extra couple of terms which you must have. And these terms you probably would not have guessed, just saying I'm going to write down some extra force terms to conserve energy. Anyhow, I just want to say something about that because it's useful. Now, I think I'm going to leave those there because before... Oh dear, oh dear. Are we still getting sound? Excellent. So, Lagrangians. Lagrangians were invented by Lagrange. He wanted equations which were going to enable him to solve all dynamical problems. He wanted to be simple. He was 19 years of age, so he thought, well, he was ambitious. The Lagrangian is equal to the kinetic energy minus the potential energy. The equations of motion are d dt, so Lagrange's equations, d dt of dl with respect to, actually I've written it with respect to a vector here, but actually you have one equation for each vector component. So I'll give it a label A, is equal to dl dra. So these are vector equations. Let me remind you again that the meaning of this is that it's a vector with components dl dxa, dl dya, dl dza, and so on. That's what that notation means. And here's an example. A 1D oscillator. and L is equal to half mv squared, kinetic energy, minus the potential energy. So there's only one component here. dl dv is equal to mv. dl dx is equal to m omega squared x. So this equation becomes d dt of mv is equal to minus m omega squared x. The m's can cancel, and v is equal to dx dt, and you get d2x dt squared is equal to minus omega squared x. So that's an example of a Lagrangian. In this particular case, it's a scalar quantity because there's only, you might think because there's only one coordinate, but normally this would be half vector v squared, so it's vx squared plus vy squared plus vz squared. And if it's a three-dimensional oscillator, this may be x squared plus y squared plus z squared. Now in fluid dynamics, there is a Lagrangian, and if the entropy is for each element of fluid is constant, it takes the form half rho v squared minus, and this is the internal energy, rho s. And s, as you now know, is the entropy integrated over the volume. So that's a scalar quantity. And I assume the entropy is constant, and I'm assuming, therefore, that there's no dissipation, no viscosity, no heat conduction. These equations assume that. But when we get it, we can then play around with it a bit. So, we want del, well, first of all, this is going to be approximately the sum over B, half, rho volume element gives me m, vb squared, minus u, now this is particle B, let me think if there's anything else I need here. This is also a rho. So I could take the m outside. And here we do. This was the internal energy per unit mass. Now it's multiplied by rho times dr, which is mass. Okay, that's the SPH form of the Lagrangian, from which you can determine the equations of motion. Now when I actually put these notes together, what's the time? 48. I worked out the details of the equation of motion. You've got to differentiate this. So dl dv a, which is what we need here. Where is va in here? It's only in one term. It's the term that has a instead of. So if it was particle 3, the only place it would come up is when b is equal to 3. So we'll have ma va. Now we need to differentiate it with respect to the coordinates. Well, that doesn't contribute anything, but this does. Used to have a b in here. Because rho b depends upon the coordinates. So what you have to do is differentiate that. Well, at the moment we've got minus sum over b mb du. Now let's do a step. I'm going to differentiate first with respect to rho b, and then d rho b dra. And now we write rho b, we use it in the form some m, I'm going to put mc. Why? Because I feel like it. So I'll use c for a label for the particles. So it's a sum. And I want to differentiate it with respect to Ra. And when I differentiate it, where does Ra appear? Well, it could be in here. Maybe Rb is equal to Ra. I mean, A might be 3. Maybe B is 3, so that would be R3. Or C is 3, so RC could be the same thing. Somebody's stretching to see this. I'm going to make your life better. So you need to differentiate this. And I'm not going to do that because you're clever enough to be able to differentiate those things. When you do, Lagrange's equations what do they give you? They give you d dt of VA, I've cancelled out in MA, is equal to the sum over B, MB, PA over rho A squared, plus PB over rho B squared, and a gradient term, because these derivatives show up in the derivatives of that, which is what we had before actually. And this just shows you how it comes about. And when I first started the SPH, as I said, I couldn't see this and I wanted to conserve linear and angular momentum. So I worried about how to put the terms together. And then I used the Lagrangian, and then this came up, and then it was easy to see that this was minus grad p on rho plus p on rho squared grad rho. That's this expression. And I didn't want to write a paper in which I started with the Lagrangian, so I just decided to write this down. But it came from this, and this is grad p on rho. This looks like a little 2 that's in there, but it's not. All right. Now that's using a Lagrangian for this, and you can use the Lagrangian for many other equations. So it's always worthwhile thinking about what it should be. You can have a Lagrangian for a system of well, let's take a simple case. 2 polytropic objects. You have a Lagrangian which describes the gas, and then you've got the mass moving around under gravity. That's some other terms which will come into the equations. And you write it down, and then you just take the derivatives, and if you don't make a mistake, you will get the equations, all the vector equations. So it really is, I think, a good thing. And there are some other things which you can also derive. I don't want to go on for too long. Well, you can use it for everything in SPH to get a good set of equations. We've used it for relativistic equations, and I've used it for turbulence. So I have SPH turbulence equations, which you can get from this. And there's also one other thing, which it's 7 minutes to. I don't want to do too much, or else your brains will melt down. In mechanics, you can find out about conservation by certain symmetry rules. For example, if you've got an isolated group of particles, then the equations of motion should be invariant to just shifting your coordinate system and putting a shift on each of these. And that means you can show momentum will be conserved. You should also get the same dynamics if you rotate your coordinate system. And if you apply this, you find out that what it means is angular momentum is conserved. This will only happen if the forces between the bodies are along the line of centers. So they're invariant to shifts. There is another one, which I'll just tell you about, but I'm going to stop in a minute. Here are a set of particles. So this is a bunch of particles, part of a much larger group, and they're moving around, and I want to show you something. Let's take a sort of ring of particles like this. And let me label one of these. We'll refer to that as a necklace. And the particles are like beads on a necklace. If I shift particle j to j plus 1, and j plus 1 to j plus 2, and so on, I won't change anything, provided when I shift that one to that one, I give it a new velocity, the velocity that was here. And when I shift this one to this point, I give this one a new velocity. This is in the fluid dynamical literature, is called the relabeling transformation. This system should be invariant to this kind of shift around the necklace, because afterwards nothing has changed. There's just a particle in each of these positions, and when I move this, I give it the velocity of this one here. It seems really too elementary to get anything out of it. But actually what you can show is that the sum around the necklace of Vj dot Rj plus 1 minus Rj, that is the neighbour, is invariant. And that is the SPH equivalent. I'll put an equivalent sign. Now the high priests in fluid dynamics, they like that. It's called the circulation. And you can show that this is, because that's invariant, the circulation is invariant. Now that's a really interesting kind of invariant property, because it means that there are infinitely many. You can make any loop in the fluid you like and follow the particles or the elements of fluid, and this integral should not change. So there are infinitely many. And we saw this SB in here. I haven't bothered to take that into account, but each particle could have a separate entropy. It has to remain constant because I'm assuming that there's no transfer of heat at the moment. But if it is constant, you'll find if entropy varies, then when I go from j to j plus 1 to make the system invariant, I have to replace the entropy of j by the entropy of j plus 1. And the entropy of j plus 1 when I shift it by j plus 2. Then you get the following. The integral around the total circulation kappa ds integrated around. So this is entropy, and kappa, now I've got to think about how I do it. I get the temperature, d kappa dt. So you get this because you differentiate this guy with respect to the entropy and have a delta S when you make the changes. And differentiating this with respect to the entropy gives you a temperature. And then you write the temperature as dk dt. Now the interesting thing about this is that if you had, say, a polytropic gas, but each element of fluid had its different entropy, then whatever motion you have in here, this should be conserved. And actually it leads to measures of the stability of the system. Now you probably don't, the high priests in fluid dynamics love vorticity because it's conserved if there's no dissipation. And there actually are some problems in astrophysics where if you think about the vorticity, you've got a collapsing cloud. Actually the vorticity can be conserved very well because the viscosity may not change it very much, and it gives you a good idea of what should actually go on. And I personally think that if I was dealing with star formation and I had some kind of collapsing cloud with turbulence, the turbulence has vorticity, the cloud can be rotating, that's vorticity, but in addition you can have a more complex field which gives you shear flow, which gives you vorticity. And then the dynamics of that system change enormously. So if I was doing it, I wouldn't just have a kind of cloud with turbulence and rigid rotation to start with. I would put in a more complex velocity field because I think the vorticity is interesting.